Hello, everybody. Good evening, afternoon, or morning, depending where in the world you are. Before I get to introducing our speaker, I'm just going to quickly go over the housekeeping that I'm sure you've heard multiple times today. If you have questions for Nitesh, please put them in the Q&A tab, and we will be taking questions throughout the presentation. So feel free to pop your questions in whenever you feel like it. If you'd like to ask a question live, you can use the raise hand feature. And of course, we have those emoticons that you can use to let Nitesh know how he's doing. So without further ado, I'm very pleased to introduce Nitesh Turaga, who is a scientist in the Department of Data Science at Dana-Farber Cancer Institute. Very excited that he joined our department earlier this year. So Nitesh, it is all yours.
Thank you, Erica. All right. So thank you guys for having me and coming to my talk. So let me just share my screen here and we'll kick it off. So I posted a couple of links in the chat and I'm hoping you guys are able to see those links. If you're not able to see them, please post in the chat, I guess, and we can help you out. Let me just take like another second. I think we have a good consensus, like 24 people. So should we get moving? I will take that as a yes. All right, so today I'll be talking about fast package installation with Bioconductor package binaries. So let me just tell you guys where the resources are if you haven't seen them in the chat. So these are the slides. This is a link to the slides I'm showing you right now. And the demo, if you want to follow along when I start typing code, is here. So you can follow along or read along the demo. So let me introduce the problem first and the solution we came up. So the solution we produced for this problem. So package installation in Bioconductor and R is usually slow because it takes a lot of compilation. It is specific to the operating system and the architecture of whatever machine you're using, and it needs to be compiled on that. So it's slow. We need to make it faster. And how do we do that? So we created binary packages. So we are able to create these binary packages as long as we know the operating system and the system dependencies on that machine. So that's the solution, which I'm going to present. So we need a controlled environment where we know the operating system, the architecture, and the system dependencies. And we already have a solution for that. It's the Bioconductor Docker images. So these Bioconductor Docker images are based on Ubuntu 20.04. That's the base operating system. We install the system dependencies needed to install all the Bioconductor packages. So we know what system dependencies are present. It's available widely. It's available on Docker Hub. You have both the devel and the release tags, and the release XY here matches 3.13, 3.12, 3.11, and so on. And devel is the current Bioconductor 3.14. These Docker images also come with an RStudio front end. So that's a pretty big bonus. So if people are used to RStudio, they can use RStudio on their browser. So as I mentioned before, these Docker images are open source, open development. They're available on Docker Hub. And this link here, if you're following along with my slide, is clickable. So if you click on if you click on it once, you'll be able to open the Bioconductor Docker page. You might be seeing a different page here because I'm logged into my Docker Hub account. But if I log out and try that guy again, you should see something like this, right? And like I mentioned, it's open development. That little GitHub link there is clickable. So you can see that these Bioconductor Docker images are available on Docker Hub. They're also available on the Microsoft Azure Container Registry. Again, these images here are clickable. So if you click on this, you'll see the Bioconductor Docker images hosted on the Microsoft Container Registry. If anyone's following Azure and their push in genomics, like this is a great resource. These images mirror the Bioconductor images almost exactly. They're probably separated by like a few minutes in updating one from the other. So it's very close. They don't lag behind in updates at all. And these Bioconductor Docker images have been adopted pretty widely around the world. They're used on the Galaxy platform. If people are familiar with it, it's a web-based platform for genomic data analysis. So you can spin up an RStudio image and you can use these Bioconductor Docker images there. It's also used in the Swiss Data Science Center with the Renku platform. The Melbourne Bioinformatics Center in Australia uses it in their Genomics Virtual Lab platform. And more recently, it's been used on the Anvil platform. Anvil is currently hosted on a private cloud, Google, and pretty soon on Azure. But Bioconductor Docker images are used within that as well. So let's talk about installing packages, because that's the whole point of this talk. So traditionally, we install packages in a very normal manner or traditional way. So we say BioC manager install, you give it a package name, and what happens then is it downloads this package from Bioconductor in the form of a tarball, and then it has to compile it on your machine. So no matter what machine you're using it on, it has to compile it. And this is the step which takes the longest time. Whereas for binary installations, when you use this command now, so we have a new function within this package called Anvil. It's called Anvil install. And when you say Anvil install package name, it does something different, which is it downloads a binary from the cloud. And the binary is a pre-compiled chunk of code, which is specific to that architecture and operating system. And here, that operating system and architecture, like I mentioned, is the Bioconductor Docker image. So when you download this binary, it's pre-compiled, and all you have to do now is point your R to look at that location, that download path. That's it. So as long as your R can find where you downloaded it, you're good to go. You can use that package. So it's much, much faster. Some packages take like close to an hour to compile, and that is completely removed with this. So let's get into the demo now. Is everyone with me so far? Any questions, comments? All right. Let's see. 1 second. So why is, all right. So are you guys able to see my, I'm hoping you guys are able to, because I'm not getting any feedback. So I'm hoping you guys are able to see my terminal. So I have this folder called demo. There's nothing inside of it. except this one folder, which doesn't matter for right now. So the first demo here is going to be about launching a Bioconductor Docker image. So we're going to first clone the Bioconductor Docker image. github.com Bioconductor Docker. And once this happens, you should be able to go into your Bioconductor Docker folder, and you'll see a file called Docker Compose. You don't have to worry about what it's doing, so on and so forth. That's a whole different talk. But like for now, we'll just learn how to launch it. So if you say Docker Compose, compose up -d, what this -d, this flag D is doing is it's launching it in daemon mode. So that essentially means that it's going to be run as a background process. You won't be able to see that it's running. You'll still get your terminal back. So when I do that, it'll say started my BioC 314 container. And this is going to be launched on my local host, which I will log into on port 8787. So you have this RStudio now, and you have RStudio as a username and BioC as the password. And when you guys want to take this Docker image down, if you're following along, you'd have to say something like Docker Compose down, and it will take down the Docker image. You can also see what else is happening. If you say Docker Compose PS, you'll see that, hey, this container is running. Docker Compose LS, I think it'll give you what Docker image is running, and so on and so forth. Great. So now we have this Docker image running. Now we have to get into our next demo, which is installing the traditional way, a Bioconductor package. So first, let's check this Docker image, right? Like I boasted about it, so I want to check like if it's all good. So we can say BioC manager valid, and this will tell us if the version of R and Bioconductor match each other, and if it's valid. And it'll also check the packages installed to see if there's anything out of date or anything too new. So here you can see the version of R, it's 4.1.0. The version of Bioconductor, you can also check with BioC manager version, and it'll say 314. So everything is good there. So now we'll just test like a simple install of a package. So BioC generics, I'm sure all of you guys have installed a package before. And what this will do is, oops, I seem to have it installed already. So I'll say force equals true. And what this will do is it'll install that Bioconductor package. Let me just scroll up here a little bit to walk through this output with you guys. So you can see that this Bioconductor package is being downloaded from bioconductor.org. And this ending here, essentially, packages / Bioconductor version / BioC source contrib, that's pointing to a CRAN style repository. And then you get that tarball, BioC generics 0.39.1 tar.gz. And then what it says byte compile and prepare package for lazy loading. So that's essentially saying, hey, I'm going to start compiling this package on Ubuntu 2004, a Linux operating system. It'll do all of that, and it's done, right? We can, don't worry about this. All this is saying is there's a couple of packages which need to be updated later on. So that was easy. BioC generics, that was fairly fast. So what's the point of producing these binaries? Let's try something a little more time taking. say hdf5 and say force equals true because I want to make sure that it re-downloads and recompiles everything. So this is going to take a minute. So here it's going to download this RHDF5 package again from bioconductor.org. And now it'll start compiling, right? All of this is R compiling the package on that machine. So that took a second, right? So, okay, so now we have a problem. So I want to say there's a disclaimer here. I hand selected these packages in the interest of time so that we're able to have like a good demo. But there are packages which I could show you guys which take forever to compile. So how does BioC Manager know where to download these packages from, right? So that's governed by what is inside this BioC Manager repositories. So here you'll see where each package comes from. So if you see the first link here, it says bioconductor.org packages 314 BioC. So, and the label here says BioC soft. So that's where the software packages are coming from. The next link is pointing to the annotation packages. The one after that, experiment, workflow, books. And then these CRAN packages are coming from something called the RStudio package manager. And those are binaries. So if I were to install a CRAN package, it would be a binary installation and it would be very quick. So we want something similar to happen for Bioconductor packages as well, especially the software ones, right? And let me point something else out to you guys. So before we go on to the next stage, I guess. So there are these things called libraries. Think of them as like physical libraries. You put all of your packages in this physical library. And whenever you want to study something, you go pick up a book from the library. Just like that, you go pick up a package or look for a package in a path. So this library path is where all of your packages are being installed. And that path right there, user local lib host site library, is mapped onto a local path on your machine. So if I look at my Docker compose file, it has this line here which says volumes. So what that means is this volume on your local machine is being mapped to user local lib r host site library in that RStudio Docker image. So if I were to look at this guy, ls that, it'll show you that I have some packages installed already, and it'll keep populating them. So that's it for that. And we're going to move on to the next part of the demo, which is essentially showing you guys how to do this in the binary installation manner. So just so you guys believe me that we're installing everything brand new, we can say remove.packages. User local lib host site library. There's going to be a couple of errors there because I seem to have some markdown files for some reason in that folder. But ignore that. That's fine. But now if we go back here, we'll see that, let me just remove these guys so there's no confusion. Not in that folder, sorry. So let's do that again. So there's no packages here. There's no packages within my lib paths. So we'll try the binary installation now. So the Bioconductor Docker image comes installed with a package called Anvil. So you can just load it without installing it. It's already there. And you can use the Anvil package. And there's a function called Anvil install. And you can say rhdf5. And this will download the tarball, a precompiled binary tarball from the Google Cloud. And it will rapidly install everything, right? So it will install the package itself and the system dependencies. All right, let's just go through the output once. So you'll see here that the download URL for Anvil install is this Google Storage APIs. So that's an object store which is hosted on the Google Cloud. And this, again, is a CRAN style repo. So packages / bioconductor version / bioc source contrib. That's a CRAN style repository. So it's looking at that link and it's getting stuff from it. And it'll download all the dependencies as well. And you'll also notice that there's no byte compile and install step here. It's just install binary package and that's it. So how does Anvil know where to get these packages from? So similar to BioC Manager repositories, we have something called Anvil repositories. And you can see that there is a label at the top which says BioC binaries, and you have the link for the CRAN repo stored on the Google Cloud. And if there's a binary that fails for whatever reason, it'll always default back onto Bioconductor. So say, for example, a certain package doesn't want to install for whatever reason, it'll go to Bioconductor, get the package, and it'll compile it on your machine. And similarly, if you install like a CRAN package, it'll look at the RStudio package manager, and it'll get the binary package for you. So there's a couple of ways you can do this. Let's look at the Anvil install function signature really quick. So there's this function called args, which will show you the arguments of a package. So if we say args Anvil install, it'll show us all the arguments you can put in. I want you to focus on this specific argument, binary base URL. So right now it's defaulting to this Google storage link, but we also have another cloud hosted binary repo. It is in Microsoft Azure. And the link for that, I just copy pasted here, is bioconductor.docker.blob.corewindows.net/packages. So you don't need to remember that, obviously. But the point I'm trying to make here is you can install these binaries both from Google or Azure as of right now. So if I were to say something like Anvil install rhdslib, just so that I have a different package to demo, binary base URL equals Azure, which is providing it that link up there, it should now take the binaries from Azure. So let's look at this link here. So you'll see that, again, this is very quick. And the download link for the binary tarball is now from the Azure blob store. And again, no byte compilation is needed here. It'll just install the binary package. Basically, all that's doing is it's pointing to it. Simple as that. And if you wanted to make sure that it works, you can say rhdslib is lib, and it'll say rhdslib. I can use some function. I don't exactly know how to use rhdslib, but we get the point. And if you wanted to give the Google link explicitly, you could do that. You could just go back to this function signature here, copy this, and you could do the same thing again. Anvil install rhtslib binary base URL, and it'll install it from the Google location, right? So the Anvil package, when you install it, it'll always install the binary no matter what. It doesn't need to be forced to do it, like BioC Manager. So whenever you say Anvil install a package, it'll just download the binary and install it. Unlike BioC Manager, which will say, hey, I already have the current package. Are you sure you want me to install it? And then you can force it to say true. So that's binary installation. Now let's do some benchmarking, right? Like we're all scientists here and we like to compare one versus the other. And for benchmarking, I usually like to use a package called microbenchmark. So since we have binaries, I'll install it from Anvil and say Anvil install microbenchmark to avoid compilation. And it'll install it rapidly. And now I can use this micro benchmark command. So I can say micro library, micro, maybe I should just copy this guy. So I'll just copy this. You know what, let me just create a script here so I can edit this command. So basically what this guy is doing is, it's going to, let me just go over this function with you guys. So what this is doing is you're calling the micro benchmark function and you're labeling two functions here, binary and traditional. And in the first part, you're saying, hey, Anvil install rhtslib. And then to compare the same package with the traditional install, you're going to say BioC Manager install rhtslib. And you're going to force it to say true because you're already installing it once. So BioC Manager won't know. And then what you're going to say here is, you know what, we're going to say ask equals false, because otherwise BioC Manager will ask us a few times if we want to install all the dependencies and so on. And the times here is basically saying, hey, how many times do you want to run this function so that we know one is better than the other? And we're going to run it 2 times. So we'll copy this guy and paste it here. Oops, I seem to have some errors somewhere. There we go. That should do it. I had an extra parentheses there, so I removed that, and we're going to try it. So it's going to spit out all the code again because we didn't say quiet equals true in either of the functions. So it's going to take a minute. So in the meantime, let me see if I can get the AirMeet thing up and see if you have any questions. Any questions, guys? Like anything at all? I see the results of my poll here. I asked people if they use the Bioconductor Docker image, and I can show you guys the result. It says only 7 people use it, and I can probably tell you who those 7 are, and then 12 people don't use it. Does Anvil install work with developer-generated binaries, say on GitHub? No, it doesn't. They have to be on Bioconductor for Anvil install to work, because we have to generate the actual binary, host it on the Google Cloud, and then distribute it to people. So that's a no. All right, let's wait some more. So you can see that it's compiling a couple of packages, and it's going to take some time now. And if you count like how many times we're installing it, it's 2 times 2. We're running each package twice, so it's 4 packages, and it's taking quite a long time. All right, so it's done. So we can see our results now. And you'll see that there's a huge difference, right? So binary here. So let me just explain the results. So the units are in seconds of this benchmarking. And then you have the binary function, and then you have the traditional function. And we can see the median, which says 7 seconds for the binary packages versus 53 seconds for the traditional packages. And the same, it's pretty close with the mean as well. Actually, it's exactly the same. It's 2. So, and it's evaluated twice. Can you? So I have another question from Leo. Can you have some anvil install packages and then regular? Yes, you can have some anvil install packages and regular install packages. So once you compile them on the image, on the Docker image, it's a binary anyway, so it doesn't make any difference. Yes, you can have that. All right, we'll move on to the next part of the presentation. So I have some better benchmarking results for you guys, which I just wanted to review this a little bit more. So I ran the same command I ran over there. So I ran it twice, but here I ran it 20 times. And I wanted to show you guys the results of that. So in the green, you have traditional, and in the blue, you have binary. And you can see that as you run this more and more, the difference keeps getting larger. Well, not infinitely, but like it separates out a little bit more. So it takes 6 seconds for the binary and 71 seconds for the traditional, right? So you can save quite a bit of time. So if you're installing 2 packages and it's taking 6 seconds on average, you're installing 2 packages a day. So that's 1 minute a day extra you're wasting installing a package. And that's 360 minutes a year. And you do the math. So let's talk about availability. So these binaries are currently available on the Google Cloud and on Azure. Going forward, we think that we're going to have more frequent builds on Azure. And this is hoping that we see a community uptake of these binaries and we actually get to serve a large community. The next thing I wanted to show you guys is a demo of the usage of these binaries on the Anvil platform. So I already have, so this is the Anvil platform for those of you who are not familiar. It's basically a cloud computing platform based on the Google Cloud right now, but pretty soon it's going to be available on Azure. I'm already logged in via my Google account. So, and a billing account, a credit card, a credit card essentially is attached to it. And there is a workspace within the Anvil platform called Fast Binary Installation of Bioconductor Packages. And there's a README file, which is specific to the Anvil. And we can launch a notebook. I should have done this before, but so essentially you can launch a notebook here, an RStudio notebook or an RStudio server on the Docker image. So this RStudio image is based on the Bioconductor image we're seeing right now. So whatever binaries you get on the Bioconductor Docker set of images, you'll see on Anvil as well. So it's going to take a minute for this to launch. I should have done this earlier, but I seem to have forgotten. But So it's only 33 minutes in. We can take some questions now if anyone has any. Okay, so I'll just go in the order they're coming in. So let me just, I don't know how to clip these messages. All right. So the next question is, so could we use this on GitHub Actions? Yes. As a follow-up, if a package is updated on Bioconductor Git, once the BBS system builds the regular binaries, how soon do they update on Anvil? So that the flow is correct. And so right now we're updating the binaries only once a week, but I'll get into that as well. We're updating them once a week, but we're hoping that it's daily. So you'll see a daily update of binaries, both on release and devel going forward, and it'll be announced. Are these also available on via biocontainer and key? So are you talking about the packages themselves or the Bioconductor Docker image? So I know that biocontainers produce Docker images for each package in Bioconductor, which is totally different from a package binary. So biocontainers, they produce a Docker image for a certain package, and that's not what's happening here. So what we're doing here is based on a Docker image, we are pre-compiling all the packages within Bioconductor and distributing them for whoever is using that Docker image. I hope that answers your question. Okay, I'll take that as a yes. Let's see if we have any updates on our polls. Nope, only 7 people use the Bioconductor Docker image even now. I thought you all will be jumping at it after this presentation. We need to wait some more. So, okay, so I'll just move ahead with my presentation. And then we'll come back to the Anvil later on. So, all right, we went through the usage on Anvil. And this here is basically showing you guys a screenshot of the workspace. For those of you who don't have access to the Anvil right now, if you ever go back to this slide and want to be able to find this workspace, you'll be able to at a later point of time. So let's talk about some caveats with these binaries. So as I mentioned, they only work on Bioconductor Docker-based images. So right now, they're available to Galaxy, Renku, Anvil, GVL, and anybody who's using these Bioconductor Docker images, right? So all you have to do is say Anvil install name of a package, and you can install that package. There is no native support for Rocker images. So the reason for that is we install a lot of system dependencies on top of the Rocker images. So we encourage you to use the Bioconductor Docker images because we think it's a step up if you're using Bioconductor. And if you're an Anvil user, there's no support for Jupyter images right now. So Anvil gives you both RStudio and Jupyter, but we make these binaries available only for RStudio right now. In the future, we think we'll support Jupyter as well. The current build rate, Leo already asked this question, which was a really good question. The current build rate or snapshot for these binaries is 1 time a week. So off the top of my head, I think the devel build is on Tuesdays and the release build is on Thursdays. I don't have a good reason for why we chose that or why I chose that, so I won't get into that. And the other, I guess, pitfall is, so we can only publish binaries for packages which actually build and get propagated through the build system. So if you're a developer and you want access to your binary package, if that package is failing, it will not be available as a binary. And more likely than not, since Devel is usually the bleeding edge of package development, if that's the case, you should use release 313 for your Docker images, and you'll get access to that package. Let me just see if we have any questions. No. So let's check if, all right, great. So let's ignore all of that. And we are on the Anvil platform. And we'll try and install a package here. This might be a little too small, so I'll make it a little bigger and say rhtslib. And you'll see that the Anvil platform, since it's running on Google Cloud, and also because it has this Anvil package available, will take the binary from the Google object store, Google Cloud Storage. And one interesting thing to note is I demoed everything on my local machine on the Bioconductor Docker devel image, which is 314. And here, I just demoed the Anvil image use on 313, Bioconductor 313. So version. And you'll see that you didn't have to do anything special between 313 and 14. You just had to use this one function, Anvil install, and it will check the version. It will do all the magic behind the scenes and give you the package, basically. So that's all I wanted to show on the Anvil end of things. We'll go back to my presentation. So I briefly wanted to go over like how these packages are built. This is pretty interesting, especially to me, because I did a lot of work behind the scenes for this. So the binaries are built on the cloud. And we use this depth-first search approach to create this package dependency graph. And if you're not familiar with the depth-first search, what that's doing is think of it as you start at the root node for a package, and you go down its dependency. So you go down every package that depends on this package S. So S, or I should go back, I guess. So D has a dependency of B. B has a dependency of A, and A has a dependency of S. So that's why since D has 3 levels of dependencies, you'll see D at the lowermost level, right? So the way we build the graph is each level, 0, 1, 2, 3 here, is the level where it's representing the number of dependencies the package has. So S has no dependency, so it's at level 0. A and H have 1 dependency, so they're on level 1, and so on. So we build this package dependency graph, and we use something called Kubernetes. Kubernetes does this container orchestration. So essentially, we go on a cloud service, Azure and Google for now, and we deploy 50 to 100 Bioconductor Docker images, and we distribute these packages at each level in a parallel fashion. So they get built and stored on the object store, which is distributing to you guys. So it's a really neat package. So I'm just, I guess, spelling out what's happening here. But all of this functionality is built into a package I wrote recently called biocube install. It's available on GitHub. So if you click this link here again, it'll take you to that package, and it's really neat. Yeah. So let's talk about the advantages here. The advantages are obvious, right? So the install time of packages are greatly reduced. And Leo mentioned this already, but if you're using GitHub Actions as a continuous integration and development platform to build and check your package, and you're using the Bioconductor Docker image, you can use a package called BioCthis, which gives you most of the things you want to do with GitHub Actions. And instead of doing BioC Manager install, you can do an Anvil install there. And this promotes this dynamic use of R and Bioconductor, even on cloud services, I guess. So the typical usage of R is you get some data, you install some packages, you analyze the data, and you figure out that you don't have some packages. So you install some more packages and analyze the data again. And it's like a continuous cycle. So we don't want to slow you down at this installing packages phase. And they're available on all Bioconductor-based package, Bioconductor Docker-based packages or images, sorry. So if you're using it privately in your institute on Singularity, you should have access to this fairly easily. And right now it's available. So if you don't belong to a specific institution with a publicly hosted cloud, you can use it on the Anvil. I want to thank a lot of people for this, especially Martin, who guided me throughout this. So this is great. Thank you to everyone, the Bioconductor core team, Vince, Rafa, and I will take questions.
Thank you, Nitesh. There's one more question. I can push it to the stage.
Okay. Should I update BioCthis to use Anvil install, or should I wait before doing so? That's a really good question. You would probably want to wait so that we have daily builds on the binaries, and that should be very, very soon. And I'll make an announcement, and I'll make sure to message you as well.
Okay. And we have another.
Do you recommend using Anvil install? Oops. Should I stop sharing my screen? Or?
No, you can leave it running.
Okay. Do you recommend using Anvil install when I'm building my own Docker? Yes, absolutely.
That is all the questions that I see, unless anybody wants to put in one last one, but we are running out of time. I see a lot of emoticons, so.
Great.
So thank you, Nitesh, for your talk tonight, and thank you everybody for attending, and we will see you at the next session.
Bye. Thank you, guys.